In addition to knowing how to draw arrow pushing in an acid-base reaction, it's also important to understand when an acid-base reaction will occur. The tool that we use to help sort this out is pKa. pKa is a measure of the acidity of a compound, and the lower the pKa indicates a stronger acid, because you're forming a more stable conjugate base. If we look at the equilibrium expression for the acid-base reaction above, products over reactants, you can see the Ka value. It's basically the equilibrium constant. We'll write that up here. If we take the negative log of the Ka value, we get the pKa. I'll give you a couple examples of pKa values. Acetic acid, which is a relatively weak acid, has a pKa of 4.75. On the other hand, hydrochloric acid has a pKa of -7. Remember, a lower pKa means a stronger acid. So HCl is a much stronger acid than acetic acid. In organic chemistry, all of this math isn't really that important. I'm more focused on whether or not you understand why HCl would have a lower pKa. Why is HCl more acidic than acetic acid? The first determinant in figuring out how strong an acid is going to be is the atom itself. More electronegative atoms are always going to be more stable with a negative charge. Give you an example, ethanol. Right here, if we do an acid-base reaction and we take off the proton, we are left with an ethoxide ion. The pKa of ethanol is 16. If we do the same thing with ethylamine, we take off one of the protons, we have a negative charge here. Both of these molecules have a negative charge. The only difference is the atom that bears the negative charge. Oxygen is more electronegative than nitrogen, so it's going to have a lower pKa. It is more stable with that negative charge. If we put a negative charge on carbon, which is very electropositive, it's very unstable. That's why the pKa is 50. It's a very high number, so it's a very poorly acidic. In addition to the electronegativity of the atom, you also have to consider the size of the atom. Ethanol, again, if we look at this, will generate a negative charge on the oxygen. Meanwhile, if we replace the oxygen with the sulfur atom, we generate a negative charge on the sulfur. You'd think, well, they're both relatively electronegative, they're in the same period, what's the difference here? Why is the sulfur-containing compound 10 to the 6 times more acidic? 10 to the 6 is a million. Why is this a million times more acidic than ethanol? Well, the difference is that sulfur is one row down on the periodic table, so it's larger, which means we're spreading that negative charge out over a larger volume. If we're spreading out charge, we're minimizing charge, we're going to have a lower energy. So, atom size is very important in addition to electronegativity. After looking at the identity of the atom itself, we should also look at resonance. Conjugate bases that are stabilized by resonance are always going to be more stable. So, if we take ethanol, we get ethoxide, O-. There's no way to stabilize that negative charge, other than the fact that oxygen is electronegative. When we take acetic acid, however, you should recognize that acetic acid has resonance. This negative charge can be shifted up to that top oxygen atom. Which essentially means that each of these two oxygen atoms are going to have half of a negative charge. If we add a third oxygen atom, in the case of methane sulfonic acid, the pKa gets even lower, down to -1.9. That's if we look at the conjugate base here. This negative charge can be distributed to either this oxygen on the right or back over to the oxygen on the left. So instead of having half of a negative charge, each of these oxygens essentially has 1/3 of a negative charge. We're spreading the electron density over more atoms, so it's going to be more stable. We're minimizing charge. Also, if you have an electron withdrawing group, an inductively electron withdrawing, inductively just means across a couple of bonds, the electron withdrawing capability of that atom will stabilize the anions. Again, let's draw the conjugate bases here. If we make acetate, here, this is stabilized by resonance, so that's why we have relatively low pKa. But when we add a chlorine atom here, the pKa drops about 2 points, which is 100 times. So this chloroacetic acid is 100 times more acidic than regular acetic acid. Why is that? Well, chlorine is electron withdrawing. It's very electronegative. So as it pulls electron density away from this general area here, it helps stabilize the negative charge that we see here. This is inductively stabilizing. If we add a second chlorine atom, it makes it about 10 times more acidic on top of that, because not only do we have one chlorine atom pulling electron density this way, we have a second one pulling it this way. So we have more pull on this negative charge, which is going to help stabilize it even more. The last factor that impacts acid strength is the hybridization of the orbitals. Smaller orbitals are more electronegative, and they're going to be more acidic. So let's draw the conjugate bases for each of these. If we deprotonate ethane, we get a carbanion right here. This is sp3 hybridized. sp3 orbitals are the largest orbitals because they're a mix of p orbitals, which are pretty large, and s orbitals. But if we look at it, we have one s orbital and 3 different p orbitals. So we have more p character here. This is 75% p, which means it's much larger than a single s orbital would be. Let's compare this to ethylene. If we deprotonate this, we have a negative charge here. This is sp2 hybridized, meaning we have an s orbital and only 2 p orbitals. So we go from 75% p character down to 66% p, which means it's going to be smaller, more electronegative, therefore more acidic. Finally, if we take acetylene and we deprotonate it, this is sp hybridized, meaning we only have one s orbital and a single p orbital. In this case, we drop down to 50% p character, which means of the 3 orbital hybridizations we're looking at, sp is the smallest. Smaller atoms like fluorine are more electronegative. Same thing here. The smaller sp orbitals are going to be more electronegative than the larger sp3 orbitals. The last thing that you need to be able to do with pKa values in acid-base chemistry is predict which way the reaction will go based on pKa values. In general, acids with a higher pKa value are always going to be formed because generally they're more stable. Their conjugate bases are more stable. So let's look at this first reaction. Which one has a higher pKa value? Hydrogen cyanide does. So reaction equilibrium is going to be forced this way. Why is that? We have to be able to think about that in terms of organic chemistry too. I don't care if you can memorize a number, I care if you understand why. Well, this H2PO4 minus, if we draw that out, is stabilized by resonance. In the case of the Cn minus, all that we have going for it is that it's sp. So we have a negative charge on a carbon, which is sp hybridized, so that helps a little bit. It's inductively withdrawn by the nitrogen, but oxygen is much more electronegative and it's stabilized by resonance. So this is going to be more stable, shifting the equilibrium to the right. Take the other example here. Water plus cyanide ion will generate HCN and hydroxide, not H2PO4 minus. So if we have hydroxide here, which one's a stronger base? Well, you should know that hydroxide is a stronger base than cyanide. Hydroxide is a very strong base. Which way is the equilibrium going to shift? To the left. Another way of doing that is compare which one has the larger pKa value. Water is. It's more stable. Okay, let's take a look at the conjugate bases and compare it in terms of organic chemistry. OH minus, we have a negative charge on the oxygen, which is electronegative, so that's okay. But in this case, with the cyanide, we have a negative charge on an sp carbon, which is inductively stabilized by the fact that nitrogen is a little bit more electronegative than carbon. So the mixture of factors here make this more stable.